All right, so before the break, we were dealing with properties of waves. So we learned terms like amplitude and crest and trough and wavelength and all of that kind of stuff. And then at the very end, we were working on the universal wave equation, okay, which is V equals F times lambda, or lambda over t. Okay, we did some problem solving with that. We said things to watch out for are echo questions, or questions where they tell you the number of crests and or troughs, okay, that have passed by an observer. Okay, and that was really the only thing they could trick you on. They could also give you the temperature of the air if it was a sound wave problem. You'd have to use that extra formula we learned. Okay, that V equals 332 plus 0.6 times temperature, okay? Or they could tell you that it's some kind of electromagnetic wave, which means it travels at what speed? Speed of light, 3.00 times 10 to the 8 meters per second, okay? So that was the stuff we covered before Christmas, right? What we're gonna look at now is wave behavior. The rest of the unit is about what kind of weird things waves can do. All right, we're going to talk about interference. We're going to talk about what happens when a wave goes from one medium to another, okay, in terms of the change in wavelength, in terms of the change in speed. Which property of a wave will never change? Frequency. Talked about that before the break too. Okay, that's going to come up a lot, right? But we're going to look at that stuff. Then we're going to get into standing waves, okay, which is actually the result of interference, okay, and then lastly the Doppler effect, which also has a bit to do with interference, okay, and that will be the last thing we cover. Okay, so that's all that is left in the unit. Okay, so interference and linear superposition. Linear superposition is the really complex way of saying what happens when two waves occupy the same space at the same time. Okay, waves can occupy the same space at the same time because waves are not matter. They are a disturbance, yes, sort of a distortion a little bit. Energy. They're energy, okay? So they're traveling through a medium, they disturb the medium, they make the medium go up or down, okay? But when they're traveling towards each other, okay, if they run into each other, what happens? Since they're not made of anything, yeah, they just go right through each other, okay? They can pass right through each other, but because each wave carries energy, something has to happen to the medium in which they are traveling in order for energy to be conserved. So let me pose this to you. What if I had this wave and this wave, and they were traveling towards each other? What would it look like when they overlap? It would be bigger. Energy has to be conserved. Okay? So when these two waves occupy the same space at the same time, the medium has to show how much energy is in that position. And it would be equal to the amplitude of the two waves added together. Okay? This is an example of what we call constructive interference, okay? Because it makes the amplitude larger. So then by the same token, if those two waves are traveling towards each other, what is the medium going to look like when they overlap? If they have the same amplitude, let's say their amplitude is +1 and -1, the amplitude of the medium will be 0. Okay? That is what we call destructive interference. So the medium would look like this. The two waves are still there. Okay? Their energy is there, but the medium doesn't show it, or does show it, okay, based on its shape. Okay? Now, will the fact that they interact with each other change them after that? Not at all. Okay? They pass right through each other, the medium does its thing while they're overlapping, and then they keep on going on their merry way, okay? Completely unaffected. Remember, they're not matter. It's not like two cars crashing together. Okay? This is energy. Energy can pass through itself. okay? And it would be completely unaffected. Okay? It's like when you cross like two flashlights. Okay? Do the beams stop because you cross the beams? Beams just keep right on going afterwards. Okay? Light's a wave. Same deal. Is it a little brighter where they overlap? It is. Okay? But that's because the energy, there's a lot more energy there at that point of intersection. The same is true for any wave. Okay? In fact, it's true for sound as well, and that's something we're going to look at later on today. Okay? If you have two sources of sound, okay, there will be places where those waves overlap constructively and destructively. If you could walk around a room with two sound sources, there'd be places where it'd be loud and places where it'd be quiet, okay, based on whether the waves are interfering constructively or destructively, okay, which we'll look at later on today. Does that make sense so far? Okay. Now, it is in fact interference that most musical instruments are designed around. Okay, interference and standing waves. If we want to make an instrument naturally or acoustically amplify sound, we need it to make the waves interfere constructively with each other to appear louder. All right? So, for example, if you strum an acoustic guitar, okay, you get a fairly loud sound coming out of it. If you strum an electric guitar that's not plugged in, do you get as much sound? In fact, you barely hear anything at all, okay? Because those waves come off of there and they're very small, okay? The ones that have come through the acoustic guitar have gone through the cavity of the guitar, okay? They bounced around inside. When they come out, okay, they're resonating and they're interfering constructively and they're much, much louder as a result. Okay? For an electric guitar, you got to turn on the little pickup microphone, okay, that picks up the waves coming off of those, and then it's electrically amplified instead. Okay, so the mammoth whistle would work the same way, okay? So like a dog whistle, if you blow on that, okay, same idea, the waves are going to interfere, okay, in such a way as to make them louder. But we can't hear them because they're above the range of frequency that our eardrum is capable of vibrating. Some people can hear it a little bit, okay, in a dog whistle, but okay, like dogs, for dogs it's like really awful, okay, but we generally don't hear it. Okay? In the same way that very low frequency sounds are not heard. We can feel them, but we don't necessarily hear them. Okay? Kind of below 20 hertz is more a sound you feel than hear. Okay. All right. All right. So, this is the diagram that I drew for you, but it's much better than what I drew. Okay, so we got the two different types of interference here. If I've got waves A and B approaching each other, okay, and they overlap, the medium has to assume a shape that is the sum of their amplitudes. It has to conserve or show that energy is conserved according to the law of conservation of energy, and then they will pass right through each other afterwards. Okay, A is now over here, B is over here, and they go right through each other. That's constructive interference. Okay, the opposite is destructive interference. Okay, so if I have wave A approaching wave B, okay, wave B is down, wave A is up, but they're the same amplitude, okay, but one is negative. Okay, when they overlap, this is what we'll get, absolutely nothing, and then okay, they will travel on as though nothing happened after that. All right, now, I do have a video of that we took one day here in class. That means I don't have to bend down and show you with the slinky. Record that as my video.
1, 2, 3.
Okay, so you can see the waves approaching each other, and then for a moment they disappear, and then they keep on traveling completely unaffected after that. They disappear a bit because of resistance against the floor, okay, but not because they ran into each other. And there, the reflections do the same thing. That semester we must have gone a little faster because he's wearing his Christmas hat. He must have got to this lesson before Christmas. Now, I think we do a constructive one in super slow-mo here as well. Yeah, there we go. So they're both going off to the left. And you can see that it clearly gets larger when they both overlap. Okay, I'll skip all that stuff in the middle there, just so you see them again here. So this one's destructive interference.
2, 3.
Okay, so you can kind of see that right there is the point where they completely overlap. If I go one frame further, they're already through each other, so they're complete destructive interference, and then they go on afterwards. Okay, and then when we do the constructive one, okay, so it pops up twice as high as each one was before, and then they go on perfectly fine afterwards. Okay, everybody with me there? All right. Okay, so the principle of linear superposition is this underlined part right here. Okay, this is what happens when two waves overlap. The medium, in the case that we've gone over, the slinky, but it could be water, it could be air, it could be anything. Okay, it is going to assume a shape that is the result of both of those things interfering, both of those things being in the same place. So it's going to be the sum of the individual amplitudes of the interfering waves. Okay. Now, we've looked at this very simply, two pulses, okay, going towards each other. Most interference is quite a bit more complex than that. Okay? I don't know if anyone has ever noticed this, but if you're using your Bluetooth headphones and you fire up the microwave, okay, what happens to your Bluetooth headphones? They crap out. Microwaves and Bluetooth headphones are on similar wavelengths and frequencies. Okay? And so when you fire up the microwave, it's likely that your Bluetooth headphones are going to cut in and out while the microwave is running. If you're standing close to the microwave, they probably won't work at all. Okay? Old Wi-Fi used to do the same thing. Okay? Old Wi-Fi used to be on kind of a similar wavelength to what we call Bluetooth now. And I can remember it was March Madness, and I had like all the round one games going. I had like a couple of TVs, laptop, computer, an iPad, and an iPhone, and they were all, so I could watch, because it was like crunch time in all of them. Okay? And then one of my kids came in, because they were hungry, you know, and they fired up the microwave. I'm like, no, because I missed like the game-winning shot for the Spartans just as they fired up the microwave. And so, you know, father of the year is like, shut that off! You're hungry. I don't care, my kid's hungry. Yeah, it's awful. I feel bad. Okay, but the point is that there was interference going on. There were so many waves overlapping, and they were nothing alike, that they just resulted in the medium, the air, what they were traveling through, was a complete jumbled mess. Okay, that none of the devices that were trying to use the Wi-Fi could make any sense of. So what do they say? No signal. Okay, so same thing with your Bluetooth headphones. Okay, that's what interference is. It is waves overlapping, okay, and their amplitudes amplifying each other in either a positive or negative way. Most of the time, we talk about interference in a negative way because it gets in the way or interferes with, okay, what we're trying to do. Right? But interference isn't always negative. We use interference to make things louder and do good things. Okay? That's what acoustic amplification is all about. Okay, questions so far on those? Okay, so we got constructive interference, destructive interference. Okay, the adding together of the individual pulses is the principle of linear superposition. Okay, so when these two go together, okay, our resulting wave a little while later is going to be a wave that's probably about that tall. Okay, the sum of those two. When these two overlap, we're just going to get a flat line, okay, because that would be destructive interference. Okay, so here's what I might ask you to do on a test with this concept and at this level. Okay? On a test, I would probably do something like this. I would say, oops, messed that one up, sorry guys. these two waves are trying to occupy the same space at the same time. Draw the resulting shape of the medium. What would you draw? First off, what kind of interference would this be? These two waves are occupying the same space at the same time. When this one is up, this one is up. When this one is down, this one is down. What kind of interference are we going to have? Constructive. They're what we call in phase. Okay? In phase means one is up, the other is up. One is down, the other is down. They're matching each other. Okay? So in this question here, the correct answer would be a wave that is the sum of the two waves that are interfering. Everybody with me so far? Okay, now if I did it differently, so let's say I've got that wave, and then I have this wave. Are those waves in phase or out of phase? They're out of phase. What kind of interference am I going to get? Destructive, right? Okay, and that means that the resulting wave would probably look something like that. Now, on a test, I would put a grid on there so you'd actually know this one's +3 and this one's -1, and you'd be able to figure out that the resulting amplitude should be +2, okay, or whatever. All right, is that a pretty easy question? Okay? Like that should be a total gimme, okay, on the test. It's 3 marks, by the way, on your test. Spoiler alert. Okay. All right. So that's how you'd be tested on just the principle of linear superposition, just the basic idea. Okay. There's kind of more complex applications that we're going to look at here. Okay. So if we're looking at these, okay. So if I've got wave A and wave B, all right, so are they in phase, wave A and wave B? Yeah, when one is up, the other is up. They are in phase, okay? So they are going to exhibit constructive interference, okay? And so they're going to show increased amplitude, okay? Whereas in this situation, okay, wave A and wave C are out of phase. When one is up, the other is down, okay? The result is going to be a decreased amplitude of the waves. Okay. All right, is there any application for destructive interference? When would we want waves to be completely out of phase and result in a lower amplitude? Think of anything that you probably use fairly often that would use that? Anybody have noise canceling headphones? Okay, anyone know how they work? Okay. So true noise canceling headphones have a microphone on the outside. Okay? That microphone picks up the sound that is ambient, that is around you. Okay? In order to cancel any noise that is outside of your headphones, it actually produces sound waves that are the exact opposite of what it's hearing outside, so that it cancels, using destructive interference, any sounds that are outside of your headphones. Okay? If you work at the airport, and you ever see those guys on the tarmac, they all have the big earmuff type head kind of earmuff things on. Those are noise canceling safety earmuffs. Okay? They have little microphones on the outside that protect them, okay, from the incredible loud sounds of the jet engines, okay, and keep them safe. So true noise canceling headphones require a microphone that's picking up the ambient noise and producing sound waves that are the exact opposite of it. That's good for you. It's bad for me, because my kid can't hear me when he's wearing his damn headphones, and because I become the noise that the noise canceling headphones cancel. Still haven't figured out a way to defeat it, but it will. It'll come to me someday. Okay, but that's how noise canceling headphones work. Okay, it is also how mufflers work. Okay, so most of us have cars that have mufflers on them that work properly. Okay, and they make the sounds quieter. Okay, so the sound basically reflects around inside the system of baffles, okay, inside of your muffler. The more it reflects upon itself, okay, the more inverted it becomes. Every time it reflects off one end, it becomes inverted and it can cancel itself. The more times it does that, okay, before exiting the tailpipe, the quieter the sound is when it comes out. Okay, if you're like the guy down the street from me, he has, I'm sure, just gotten underneath with the Sawzall and just cut that right off. Okay, because he drives around, okay, and makes a show of himself, okay, all the time because he's deafening, okay, as he drives through the neighborhood without the device used to cancel the sound of his very loud engine. All right, sort of making sense? Okay, if you've ever done any upgrades or mods on your vehicle, okay, one of the things you do to increase its performance is to take the stock muffler, which makes your car quiet, off and put on one that is lower restriction. That is, it allows the air to get out more easily, which means it doesn't quiet it nearly as much. Or maybe you really like the sound of your car and you want it to sound louder, and you put on things like glass packs and things like that, okay, that can actually help to increase the quality of the sound of your car. Okay. Questions there? All right. All right, so here's kind of what we're looking at. So if I've got two speakers and they're producing just a tone, so a single tone of sound, right? And I stand equidistant from both speakers, right? I will be at a point where I experience constructive interference because I'm the same distance from both speakers, and the sound waves that they produce are going to meet at exactly the same point at that point. Okay, so in this case, we're saying that if I'm 3 meters from the speakers and they're producing a sound that is a wavelength of 1 meter, each set of waves is going to travel 3 wavelengths before they reach me. Okay, which means they're going to meet crest to crest, trough to trough, and always interfere constructively. All right, everybody okay with that idea? What if I backed this speaker up 1/2 meter? I stay put, but that speaker backs up 1/2 meter. What's going to change?
They're going to be out of phase.
They're going to be out of phase because now the sound waves from that speaker are not going to travel 3 wavelengths. They're going to travel 3.5 wavelengths. And 1/2 a wavelength from a crest is a trough. Okay, if I'm looking at a wave, okay, so this is a complete wave. Here's the crest, here's the trough. That's 1/2 a wavelength apart. So if I make waves from one of those speakers travel 1/2 a wavelength further, they're going to be completely out of phase. Okay? And I'm going to hear nothing at that location. Okay? Now, would I actually hear absolutely nothing? Not in a normal room, because there's always a reflection off the walls and things like that. You ever notice how if you listen to yourself recorded, you sound different than you sound when you're talking? I notice it because I do this all the time. I hate the sound of my voice on here. I'm really sorry, guys. My voice is awful. Okay? But your voice sounds different to you because there's reverberation within your own head and your sinus cavities and things like that, along with the fact that you hear your voice after it's reflected off of all kinds of different surfaces as well. And that changes it a little bit. And so how we perceive our own sound is different than how people who hear it directly perceive it. Okay? Now, if I was in an anechoic chamber, okay, that couldn't produce any reflections off the walls, what would I hear standing in that position?
Nothing.
Absolutely nothing. Okay? It would be completely silent at that location. Okay? Because the waves would completely cancel each other out. Okay? Now, there aren't a lot of anechoic chambers out there. Okay? A truly anechoic chamber actually looks like the inside of a meat grinder. Okay? There's lots of like jagged, pointed, irregular edges. Okay? Because we're trying to limit things having flat surfaces that waves can reflect off of. Okay? All right. So if we moved this back 1/2 meter, we would get destructive interference because now this one would travel 1/2 a wavelength further. Now, what if I backed it up a full meter instead of just 1/2 meter? What would the person hear then? Now the waves from that speaker travel 4 wavelengths, and the waves from the other speaker travel 3. are they still gonna be in phase? Yeah, they're still gonna meet crest to crest and trough to trough. The ones from the other speaker have just gone a full wavelength more. Okay, but it's still a full wavelength. As long as it's a full wavelength difference, one wavelength, 10, 200, it doesn't matter. They're still going to arrive in phase. Okay, but if I back it up another half a meter, they'll be out of phase again. Okay, and the same is true. If the difference in travel is a half a wavelength, 1.5, 10.5, 200.5, then you're going to hear nothing, because they're still going to be arriving crest to crest, or sorry, crest to trough all the time. Okay? Everybody all right with that idea? So that's where this kind of is going to get into a little bit of geometry. So if this is a two-speaker system in a room, okay, what would I hear if every one of these lines represents a crest? What would I hear standing right there, loud or quiet? Every line represents a crest. I'm standing at a point where two crests meet.
It'd be loud.
It'd be loud. Okay? What would I hear right here? It's a trick. Also loud. Because right there, okay, is halfway between. So if I put dotted lines in for each one of these waves, okay, so this would be the ones from speaker B to represent the troughs. Something lighter blue. Okay, those are meaning trough to trough. Okay, is that still in phase? Still loud.
Would that be the same volume as the crest to crest?
Absolutely. Yeah, it doesn't matter whether it's up or down. Okay, I would hear a greatly amplified trough and a greatly amplified crest. And in fact, for a sound wave, it's actually a compression and a rarefaction. We just use crest and trough analogously. Okay. All right, what would I hear if I was standing instead here? So I'm at a crest from speaker B, but a trough from speaker A. What do I hear there?
Nothing.
Nothing. That's a point of destructive interference. So let's say this is a home theater system that I'm setting up. Do I want to put a chair there? Probably not. That person's experience in that home theater would be pretty crappy. Now, this is simplified because we're only producing a single tone. Your home theater system is obviously producing all kinds of different frequencies of sound all the time. Okay? But that would be a point for at least that wavelength where no sound would be heard. Okay? Now, how many people have ever gone to a concert at the Saddle Dome? Okay. Anyone ever gone to a concert at the Winsphere in Edmonton? Okay. Those are two very different concert experiences. Okay. The Saddle Dome is probably one of the acoustically worst shapes you could have possibly designed, okay, as a concert venue. All right, the roof dips in the middle, okay, there's chairs everywhere, there's all sorts of rough reflective surfaces, okay, it is like one of the worst things you could do in terms of making good quality sound. So what do you do at a concert? You just crank everything, you put tons of speakers in there and you crank them all as high as they will go, so it's just loud, okay. If you go to the Winsphere, most of the time at the Winsphere, they don't even use microphones or pickups. That place is designed to be acoustically perfect. Okay? Any sound produced by someone on the stage reflects off the walls in such a way that it doesn't matter where you sit in there, you hear high quality sound. Okay? It took years to design and build, okay, that concert hall, but it's something pretty different, okay, in terms of performance. Now, it's not nearly as big. Okay? You can cram 20,000 people in the Saddle Dome for a concert, okay? But I think you can only put about 1,500 people in the Winsphere. Okay, so, you know, Taylor Swift is not going to be doing a concert there. She won't make any money. All right. Making sense so far? Okay, so this is something that goes into the design of home theater systems. If you're getting one custom built, they'll want to know the dimensions of the room. Okay, when they set it up, they will probably make, you know, if you've got speakers at the back, okay, as well, and the center channel, they might have to set up delays from some of those speakers for certain frequencies in order for every seating position in the room to have a good sound experience. Okay, if you go to the movie theater to watch a movie and sound is going to be important, let's say you're seeing like a superhero movie or a sci-fi movie where there's going to be all sorts of special effects, where do you want to sit? Where's the best seat? Right in the middle. Okay? If you are right in the middle, okay, you are going to have the best chance of getting the best sound experience in there. Okay? If you're sitting more to one side than the other, like a lot more like against one wall, okay, it's not going to be as good because you're close to the left speakers, the right speakers, and far from the other side. You won't get that stereo effect nearly as well. Okay, that opportunity for constructive interference isn't going to be there as much because the waves are traveling further from one side than the other. You're better off to be in the middle, okay, if you're wanting to really enjoy that sound experience. Okay? Okay, so this was the situation we were talking about a minute ago. If I back this speaker up half a meter, which happens to also be in this case half a wavelength, now these ones travel 1, 2, 3 and a half wavelengths, where these ones are only traveling 1, 2, 3 wavelengths, so they meet completely out of phase, and that would be completely quiet there. Okay. All right. Okay, so in general, okay, what determines whether you hear a loud or a quiet sound is the difference in the distances traveled by each wave when they overlap. And by distance, we should probably write in there, okay, the number of wavelengths. Actually, I'm just going to put lambda there. Okay, the number of wavelengths traveled by the waves is what determines whether you hear a loud sound or a quiet sound, or whether constructive interference or destructive interference occurs. Okay, and we can clearly see that on this picture here. At this point, okay, the speaker, the waves from this speaker here, we'll say this is A and this is B, okay? The waves from this speaker have traveled 1, 2 wavelengths. The waves from speaker B have traveled 1, 2, 3 wavelengths. What's the difference in travel? From speaker B, they traveled 3. From speaker A, they traveled 2. The difference is 1 full wavelength. As long as the difference in the number of wavelengths is a full wavelength, you hear a loud sound. Okay? If we're looking at this position here, okay, from speaker B, we've got 1, 2 and a half wavelengths, whereas from speaker A, there's 1, 2, 3. Well, 3 minus 2.5 is 1/2. Okay, they're completely out of phase. That's how you figure it out. Okay, you subtract the 2. You get the difference in the number of wavelengths traveled from each source. If it's a half a wavelength, completely destructive. If it's a full wavelength, it's completely constructive. Anything in between, then you're getting some kind of lower quality sound than you would at the highest point. Okay? Everybody all right with that? So here's where the math and the geometry kind of come into play. Okay? I'd like you to copy this one down because we're going to use this as our example of a 2-speaker question, which you are definitely going to get on your unit exam. Okay, I'll give you a minute to get that one written down. Okay, so in order to answer this question, the first thing I have to understand is what determines whether this person hears a loud sound or a quiet sound is the difference in the number of wavelengths traveling from each source, that is from each speaker. Okay? So in order to determine whether he hears a loud sound or a quiet sound, I need to know how many wavelengths are there from this speaker, okay, which we'll call speaker A, okay, to the person, and how many wavelengths are there from speaker B to the person. Now, if I'm going to find that out, what do I need to know? what would be one really useful thing to know if I'm trying to find the number of wavelengths from one speaker to the person?
The length.
The wavelength, yeah, I kind of need to know the wavelength. Okay, that's pretty important if I'm going to determine how many wavelengths there are. Okay, now in this question, they give me some distances, but they also tell me the frequency of the sound is 214 hertz and the speed of the sound is 343 meters per second. Okay, so I know the speed, 343 meters per second, and I know the frequency, 214 hertz. What can I find with those two things? I can find wavelength using the universal wave equation. Remember I told you it was going to come up again and again and again? Okay, so if V equals F times lambda, and I know both of these, lambda is going to be V divided by F. So 343 divided by 214. I'm at the 1.6. Okay, 343 divided by 214, yeah, 1.6. Okay, so the wavelength is 1.60 meters. Okay, so I need to know whether, or how many wavelengths there are from speaker A to the person. And I know that that's 2.4 meters. If I know each wave is 1.6 meters long, can I find out how many wavelengths there are? What do I have to do with those two numbers? Each wave is 1.6 meters long, and there's 2.4 meters between the speaker and the person. What do I do with those two numbers to find out how many waves there are?
Divide the distance by the wavelength.
Right. Divide the distance by the wavelength. Okay, so if I say, all right, 2.4 meters divided by the length of one wave, 1.6 meters, and pretty sure that comes out to 1.5. Okay, 1.497, that's 1.5, that's close enough. Okay, so there's 1.5 wavelengths from this speaker to the person. Now I need to figure out how many wavelengths there are here. What do I need to know first? I already know the wavelength. What don't I know about speaker B and the person? I don't know the distance. Can I find it? I just have to use Pythagorean theorem. Right? So I've got to figure that side out. So square root of 3.2 squared plus 2.4 squared. All right, that side's 4 meters long. All right, if I want to know the number of wavelengths, I'm going to go 4 meters divided by the wavelength, 1.6 meters. All right, 2.5. All right, so there's 1.5 wavelengths here. There's 2.5 wavelengths here. Does that person hear a loud sound or a quiet sound? Loud. That person hears a loud sound because 2.5 minus 1.5 is 1. Okay? If there is only one wavelength difference, then that person is going to experience constructive interference. Okay? So we would have 2.5 minus 1.5 equals 1 wavelength. That means constructive and loud. Okay. Is any one part of that question very difficult? Okay. You have to do the universal wave equation once. You have to do Pythagorean theorem once. You have to divide length by wavelength twice. And then you have to subtract those two numbers. Okay? There's nothing mathematically challenging about that question, but it does require you to understand what determines whether they hear a loud sound, how to determine how many wavelengths there are, okay? How to determine the difference in the wavelengths, and then get constructive or destructive from there. Okay, that's going to be at least a 5-mark question. And I always put one of those on the unit exam. In fact, I always put one of those on the final exam too. Okay? So that example there is pretty prime in terms of something you definitely need to know. Okay? Okay. Now. Okay. Give this one a try. Sorry, it takes me a while to make one of those up because I actually have to back check all the math before I do it. Okay? So, give that one a try. Similar to what we just did. Okay? See if you can get it. All right, so the first thing we probably want to do here is draw a diagram of the situation. Okay, so we've got this speaker, and we know that this distance here, okay, is 7.71 meters. That's how far apart the speakers are. Okay, the observer, we're told, is 6.9 meters directly in front of one of them. So. Whoa, I don't know what's going on with that person. He's got like a compound fracture or something. I want the eraser. Start my stick man over. See, my artistic ability is so bad I can't even draw a stick man. There. Okay, 6.9 meters. Okay, and we know the frequency of the sound is 147.8 hertz. Okay, and the speed of the sound is 340 meters per second. And we want to know whether the person hears a loud or quiet sound. I got to calculate 2 things before I can even get to that. What are they? Wavelength. Okay, I've got to calculate the wavelength. So if V equals F times lambda, lambda equals V over F. So 340, okay, divided by 147.8. Going to give me around 2.3. Right, 2.3 meters. Okay. What else do I need to calculate?
The person's distance from the second speaker.
Right, I got to use Pythagorean theorem to get this side. Okay, so to do that then, we're going to have the square root of 7.71 squared plus 6.9 squared. All right, so that side is 10.35 meters. Okay, what's my next step? Now I know all the sides and the wavelength. I need to know how many waves from each speaker to the observer. Okay, well if the wavelength is 2.3 meters, 6.9 divided by 2.3 is 3. Okay, everybody with me on that? Okay, so I know that on this side, there are 3 wavelengths because 6.9 divided by 2.3 is 3. Okay, so there's 3 wavelengths from the first speaker. Now I need to do the same thing with the 10.35. So I divide the distance by the wavelength, okay, which we said was 2.3. That's a 3. Okay, so I'll take the full numbers here just so that we get all of it here. So that number divided by that one. Okay, 4.497. Is that 4.5? Close enough to 4.5? Okay. Okay. 3 wavelengths from this speaker, 4.5 wavelengths from that speaker. 4.5 minus 3 is 1.5. Okay, so 4.5 minus 3 is 1.5 wavelengths different. Okay, so essentially what we're seeing here is 1, 2, 3 waves. Okay, and then from this one here we would have 1, 2, 3, 4.5. Okay, so they're not meeting at the same point. This one's a trough, that one's a crest. That's complete destructive interference. They don't hear anything at that position with quiet sound. Okay, that's what you're going to get on the test, something similar to that. Okay, all right. Got a couple more here that I'll type because typing is neater than my handwriting, which is getting worse and worse. So. Okay, so there's your question. Two boats are 30 meters apart on the ocean. They bob up and down every 4.5 seconds. Okay, I don't know why there's a space there. Okay. Every 4.5 seconds. Okay, when one boat is on a crest, the other is in a trough, and there is one crest between them. Okay, what is the speed of the waves? All right. This would be more like what we did before Christmas using the universal wave equation. Right? My suggestion would be draw a diagram, okay, in order to do this one. Okay, so first thing you should do is draw a picture of this. So here are my waves. Okay, the first boat is here on a crest. The other boat is here in a trough, and there is one crest between them, and the distance between them is 30 meters. How many wavelengths between them? 1.5. Okay, there are 1.5 wavelengths. The distance from here to here, the distance between any two successive equal points on a wave is 1 wavelength. Okay, and the distance between a crest and the trough is half a wavelength. Okay, so you have to have some understanding of wave properties and structure, okay, in order to do this question. So I know that 30 meters equals 1.5 wavelengths. How do I get the wavelength? Divide 30 by 1.5. That'll get me lambda. Right? So if I go 30 divided by 1.5, I now have the wavelength. Well, not 15, 1.5. Okay, so I get 20. All right, so the wavelength is 20 meters. All right. They tell me that the boats bob up and down every 4.5 seconds. What did they give me with that? Not frequency. Well, I could get frequency from it, but directly they told me how long it takes for the wave to make one cycle. Okay, if I bob up and down in that boat completely in 4.5 seconds, I've completed one cycle of the wave, which means that the period of the wave is 4.5 seconds. Okay, so again, that's a vocabulary test, okay, on that question there. So if V equals lambda over T, which is the other way to write the universal wave equation, okay, I now have everything I need. 20 divided by 4.5, I believe, comes up to 4.4 meters per second. Okay, so the speed of those waves is 4.4 meters per second. Okay, is there any difficult math in that? But you have to understand a lot about waves in order to do that question. That's the kind of question you're going to get. Okay, all right, I'm going to type one more up here, see how you do with that one. guys, I'll bring that back down in a second. Okay, we'll give number 3 a try there.